locally analytic assumption.
Okay, we are on.
Locally analytic complex
Huh?
Can you start? Yeah. So, before I'll ask you what you decided in the break, I'm sure you talked about it. I'll just say there's a conjecture by Seymour, which says any homological, so every code constructed in this manner is called a quantum homological code. So when I said quantum homological code, I mean codes constructed in this way. So every quantum homological code
for I equals 2 or for
any I, so yeah. So each complex gives you D codes. Yeah. And when we encoded in I just want to mention, first of all, maybe I didn't mention, but when I said the torus, I meant that these are actually filled. This is just an important remark. And the way we think of it is we say that we encoded our information in the topology of the torus. This is how we think of it. So Alice sends Bob the information. Each bit could have noise, but the information is protected in a much more global way, and somehow it's the homology is so. This is actually a map from the. This will be the logical bits, the ones that you actually want to protected. K is the homology group, and so it's protected, and that's why you need the distance is n, because in order to this is a loop, you need to go far. You need a lot of errors that you'll get mixed up and you think that this loop exists or doesn't exist. But if this is flipped and this is flipped and this is flipped, you don't care. Okay? So the conjecture is any quantum homological code suffers from the inequality k times d squared smaller than n. In particular, this means that there are not only that there are no good homological codes, there are even all homological codes are here. Let's take this, but let's plug this one in. K here is 2, D is n, so n squared smaller than n to n squared. So what he says is that the Tor code is optimal. Okay, and this was a conjecture by Seymour. Fataya was a student of Lubotsky, proved that this conjecture is true for surfaces for dimension 2. So in case this is a 2 complex, this will always hold, just like the torus. But now this is where Guth and Lubotsky. This is false in higher dimensions. So we have hope to get good homological codes. It doesn't mean that if it's false, it means it's already a good code. It just means it's not a terrible code. We have hope. It broke this conjecture, so it gives you much more hope that you could find good codes. And we'll talk about it soon. What's your decision?
My vote is for quantum.
Huh?
Yeah. Maybe take a vote.
Huh?
Take a vote.
Okay, who goes? There's quantum and there's not quantum. Who goes quantum? What is not quantum? It's going on to. It will start resembling more midrasha. Let's say it that way. Okay, so who goes quantum? Okay, we go quantum.
For the record, I want quantum. I thought that we might postpone it for later, but that's fine.
It's also an option. We can do it. I think it's just that the.
Go ahead.
Okay, let's do it. Okay, I know what I'm gonna do. I'm gonna do just one step further, not in the from here on, and then I'll describe the quantum setting and how this makes sense. So we're not so far from, but I want to keep this. Okay. So first of all, we can be more specific here. What they did here is they constructed 4-dimensional hyperbolic manifolds. So the construction of Lubotkin groups that showed this conjecture is false was by creating simplicial 4 complexes, which are triangulations of 4-dimensional hyperbolic manifolds. Okay? Yeah.
You say that like every linear code you can describe as a graph.
No, I didn't say
No?
that.
You can't?
There's a very simple characterization of which linear codes come from graphs. Which
Okay.
linear codes are
Can't
homological.
you just take all the words to cycles or something like this?
If you'll think about, I don't remember exactly now, but if you'll take a graph and create from a code, you'll see that all the codes you constructed have some basic property, some local property. I don't remember exactly what it is, but it's not all linear codes,
Okay,
not
okay.
all homological codes.
But they are-
Linear codes are homological codes.
And
And, yeah.
what about other higher dimension?
What about higher dimensions?
Yes, I mean other than 4.
So this is a pretty recent result. It's 2013. It's a good question. What happens in higher? Like part of what me and Nuri are trying to do is to ask this to improve this result to other things. Could be that higher dimensions will be needed. So there's nothing. There are good reasons why in 4 this improvement. Like okay, first of all, we see that in 2 you can't do it. So in some sense, 4 is the next step because 3 is a little bit problematic because you want we're talking about both homology and cohomology. So if you'll have 3, you have to decide if to encode it in the first level or in the second level, and it will be much more optimal to have it somewhere in the middle. So 4 is the first place where you're higher than 2 that you can do it. Okay. So what did Lubotkin Codes do? First of all, we want to now go. We started from codes and we reduced it to a purely combinatorial problem. This is just complexes. The problem here says you want to find good codes. It's enough to find good simplicial complexes, or what is good simplicial complexes, or families of simplicial complexes of growing size, where as we grow, we have more holes or more the homology group grows bigger, but you're not allowed to have small, non-contractible I cycles. Okay? But now we want to make it completely a geometrical problem. Okay? So if we have a manifold M, okay, this has a triangulation X, and this gives you a code. Right? So every manifold in a some sense gives you a code, of course many codes, because you can choose many different triangulations, okay? Now this will have some parameters, this code. And let's talk about n. So n is the number of I cells. So this depends already on the triangulation, okay? But let's say that this is kind of like in some way the volume of the manifold. You'll take a double manifold, you'll need like the volume of the manifold will be twice as big, you'll need twice as many cells to make it, approximately. K, we know K is the dimension of the ith homology group of X, but this is the same as the ith homology group of our manifold. So in this sense, there's no reason to talk about complexes because the manifold, all the topology comes from the manifold, okay? But regarding the distance, it's already much more tricky because in the distance, this is strongly related to the actual triangulation. Okay, so for example, if we have the torus, and we can choose all kind of triangulations for it. So we can choose a triangulation where here 2, 3, 4. Here the systole, the shortest loop here is 4, and we can choose, and maybe we can choose different triangulations, and we'll get this. The point is that D highly depends on the combinatorics. Okay. So if we want to move away from combinatorics and talk only about geometry, we need that, first of all, we won't take just a manifold, we'll take a Riemannian manifold, so we can talk about distances. And when you have a Riemannian manifold, if M and G, if M has a metric G, so the term systole and cosystole, which we talked about it in terms of complexes, which is really lengths, discrete lengths over a graph or a complex, we have the same notions in a manifold. So the systole, the isystole of a manifold M is equal to the length, to the minimal length of a non-contractible I cycle. Okay? And right now there is no correspondence between this and this. We start with a Riemannian manifold. If we choose just any triangulation, we have no guarantee. It could be that there is somewhere that the systole is very large, but for some reason the triangulation chose to just do it with two edges or one edge, and then the systole will be very short. So we want that the triangulation will reflect the geometry of the manifold. And this brings us into something called a Lifshitz triangulation. And basically, so first of all, what we are actually talking about, because we're always talking about families of codes, we're actually talking about families of manifolds. Okay? So if we take a manifold and we take some triangulation, so maybe, let's say each edge, which is just one edge, has a length in respect to the Riemannian metric. So let's say this has edge 4 and this 3, this is 4 and this is 5, etc. But because it's all finite, so there will be some lower bound. And up to a constant, we can say that the length of we can, I don't know, like, there will be some, let's say all edges are at least of length 3, so this gives us some kind of correspondence. But then when we take more and more manifolds, this could change. We get different triangulations, and we want some kind of uniform bound of what's the length of each edge, or the volume of an I cell. Okay, it's clear why we're looking for this? Yeah? Okay. And
you're assuming that the manifold has triangulation.
so I'm not assuming. I'm trying to state another theorem, which is a geometrical version of this theorem, and I don't want to talk about complexes anymore. I want to talk about manifolds. What I'm trying is to construct a new theorem where the word complex won't appear. There'll be only just manifolds, and then there'll be the word systole in the context of manifold. But in order for this theorem to actually be true, and if I want to prove such a theorem from this theorem, I need to kind of connect I call this the combinatorial systole to the geometrical systole. Okay? So how can we do this? So for now we're doing like it's two.
Sorry to interrupt again, but so you're going to give a definition of the systole independent of cycles?
So yeah. So okay, for now, okay. So an isosceles is for choose any triangulation, and then you can talk about isocycle, and then you can talk about the lengths with respect to the metric. Okay. Okay, so let's start with a manifold. And what we actually want is a sequence of manifolds. And there's a very natural way to create sequences of manifolds. It's by covering spaces. So we can take covering, but we always take finite coverings because this will be a compact manifold. We want everything to be finite. This will be a finite covering, so this will be a compact manifold, etc. And this is how we'll have a sequence of compact manifolds. Now the important thing is that once we fix, this is let's call this M0, and this has a metric, G0. And let's choose any triangulation, X0. This structure lifts up to all the levels, okay? Because now if we want to define, if this is P, and we want to define a metric here, G1, all we need to do is just to push it here. This will be the pullback metric, because the metric here will just be the same metric as here. Same for the triangulation, okay? We can lift this triangulation to triangulation to all levels, okay? And the important thing is that if here each edge, let's say the shortest edge was of length 3, this will be true for all the covering, okay? Because a covering, we basically think of it as some kind of just many times our manifold, of course in some nice way, but locally it's just the same. So the point is that up to some constant distortion, and we're interested only in the asymptotics of the code, up to some constant distortion, the systole, the combinatorial systole of any triangulation we chose here, up to a constant will be the same as the geometrical systole. And this will allow us to stop talking about complexes, and I'll state this as a theorem or a proposition. So let M0 d-dimensional manifold with metric G0 and triangulation X0. Suppose M is a cover space, covering space. And let Gx be the pullback metric, or in this case triangulation, from M0. So so the distance of Cx, this is the code constructed from X, each complex gives us a code, satisfies D is at least the systole, and here if this is a geometrical systole, it's just the systole of the isystole of the manifold M, or the cosystole, because this is just how we have from the theorem of M, minimum, times some constant. And what's very important is that where R depends only on M0, G0, and X0. This means
now it's a regular code, not a quantum code?
No, everything is now quantum code.
And I is fixed.
Yeah. So
does it work like for any I? Yeah.
For any I, yeah. Of course, if you take IB0 or I equals D, you'll get the empty code, which is not a code by definition actually, but
it works for all I's.
Yeah, it works for all I's. Yeah, you just choose the I. This is very important because this means all we need is to start with some compact manifold, just take a triangulation of it, and take sequences of covers. We don't need to worry at all about the triangulation we chose. Of course, the triangulation we chose, a very bad triangulation, this constant will be very bad. But it will be the same constant all over, so the asymptotics, the questions of whether the rate is, if it's a good rate, the definition of good codes won't change here. Okay, because we're talking only about asymptotics. So, is this clear? I didn't show a proof, but it's almost, this theorem proposition is almost a proof in a way.
Is this, am I taking cosystole because maybe my systole disappears and get my cosystole?
You're asking why we take consistoles? For that we'll need, if we'll talk about the quantum, there's, basically the reason is that to make a quantum code it's a bit harder, and you need more things to protect your information, so you kind of protect it, it's harder, you need both the homology and the cohomology to satisfy properties. Okay, one sec.
just to explain it, once you have a manifold, you have its inner geometry. We think about it as a smooth manifold. If we triangulate it, if we triangulate the sphere, we might get the, I don't know, the two skeleton of a tetraeder. It's definitely, it has a different geometry. Thus, since there are two compact manifolds which are diffeomorphic, then obviously there are Lipschitz equivalent, but the Lipschitz constant are bad, or might be bad, depending on our actual triangulation. But once we do fix the triangulation, and if we fix it fine enough so every simplex sits in one of these neighborhoods of points which lifts homomorphically into covers, this triangulation will be lifted to whatever cover, and the constant and the Lipschitz constants will be the same. I mean, both the metric and the triangulation will be lifted to whatever cover with the same Lipschitz constants. So when we do study families of covers and asymptotics, those Lipschitz constants are not going to make any actual change on the asymptotic rates. And this observation is behind this theory. So we can completely now shift our point of view from simplicial complexes to manifolds and their inner geometry, and forget where we did came from, and turn to apply our geometric skills.
Do we still need the triangulation to talk about the systole?
So no, we don't need the triangulation. The systole, the way you define the systole of a manifold, you consider all triangulations. Once you have a triangulation, you have a notion of I cycle, and you can ask what's its length. You take the infimal of that.
To be precise, talking about one systole, if we have a compact manifold, a surface state, with a metric, with an Riemannian metric, the one systole will be the length of the shortest geodesic, which is something very clear geometrically.
So in general, it's the volume of the smallest volume of I-dimensional submanifolds.
Yes, exactly. Which represent a non-trivial cycle in homology.
It's the least volume of I spheroid which you can embed in your manifold, which is non-contractible.
Oh, it need not be a spheroid. It could be a surface, say. If you talk about.
I'm not sure if you embed a torus.
If you embed a torus in a manifold, it represents. If you embed any submanifold, it will represent a cycle.
Okay, you're right.
If you take hyperbolic manifolds, you will not have non-contractible spheres.
You'll have only tori?
Or higher dimensional. Our genus surfaces.
Yeah.
Sorry.
Okay. Okay, and just one more remark about, because I didn't describe exactly what's Lipschitz. All I'm trying to say is that this R is a measure of how much the distortion rate between the edge of how many edges and the actual length, the metric of the manifold. This is all this is. Okay. Let's see. Okay, just two things. First of all, we can change this because we're now considering manifolds. Poincare duality will tell us that taking the cosystole is the same as taking the D minus I systole. And therefore, if you also choose the exactly intermediate homology group, it means we can erase this and consider only this, because I and D minus I will be the same. So this is another cool thing. And another thing is that these will always be LDPC codes. And it's because you won't have like, it's not like with a graph with a very high degree. We have something kind of, it doesn't matter. I didn't really define LDPC code, so this is good enough. And, okay.
But basically this is due to the fact that due to the homology you have cohomology. And if the homology has, I don't know, so many cycles as bases, the the dimension of the cohomology tells you how many checks do you have to perform on the space of all chains in order to know that something is a cipher.
That's true. Yeah.
Yes.
Okay, then you take some.
It's because, another way of saying what you said, I think, is that the co-boundary is generated by by vectors of a bounded support. This is the reason. So one more thing here that just relates to this. So I'll state now the theorem of Lubotsky and Guth. There exists a family of hyperbolic four-dimensional manifolds MJ satisfying 1. The second homology group of each one is like the volume, and we said that the volume is kind of like we think of it as our n, because you can always take the manifold and double the volume and then double the amount of cells, the amount of edges. So we think of this kind of as a representative of n, mj, up to a constant, which in their case it's enough to take 1/100. So the point is, the second homology group grows linearly with the volume of the manifold. Very good. 2. The systole, the 2 systole of MJ is larger than the volume of MJ times some constant C to the power of 0.3. Okay? And the corollary, there exists a family of LDPC, because they're always LDPC, it just means it's a good property, you think of it that way. N, K, D quantum homological codes, where K is linear with N, and D goes as N to 0.3. If this would be also linear, that would solve the problem, but this is not linear. But this is still by far more impressive. I should mention that this is not the best code, quantum code. Wow. That's intense. So this is not the best quantum code. It's almost the best. Like, there are just slight improvements, but they're not homological codes. So there are other constructions of code. We don't only need to discuss this framework. But this is definitely the best homological code, and it definitely puts it in the race of finding good.
What is this manifold? What is this manifold?
What is this manifold? Okay, so I thought to talk about it. Okay, I'll just mention what it is. So this manifold is basically take hyperbolic space, four-dimensional space, quotient it by, this is not what quotient it by, okay, so we have gamma n, but take 3, but take only Jesus. Take this group, but take only the integer values in it in order to obtain a lattice.
So on 4 or 3?
This is 4. I don't know. Should this be 3 or 4? Yeah. Okay. 4. And this is a lattice. This is a lattice here. This is actually not a good one because it's not going to be co-compact. Okay. Instead, they consider this SO14 is the set of matrices that preserve the form, the quadratic form, squared.
With the yellow bright side.
Yeah. You get some competition here.
What?
You get some competition.
Yeah, exactly.
By nature.
So what is SO14? By definition, it's the set of matrices that preserve this form. There's a nice trick that if you change this to this form, and you do another trick, maybe I'll have time to talk about it. Definitely if I'll talk about quantum stuff, I won't talk about it. But it's a variation of just what's the most ordinary lattice you can choose here? You have the group of isometries this, take the integer values. This gives you a discrete group. Quotient by discrete group, you get a manifold. And this is not a compact manifold, so this doesn't work, but if you do some variations of this, you will get a compact manifold. In order to get the coverings, all you need is to take subgroups of this. A sequence of subgroups will give you a sequence of coverings of this space, and this is basically the construction. But I would definitely won't have time to get to it.
So maybe you can explain the idea of a principal
okay, so
subgroup?
yeah, if I do that, I won't have time definitely to talk about the quantum.
You will have, not today.
Okay. Okay. So let's take. First of all, let's recall that if we have a manifold and we consider all coverings, we get this kind of lattice. It's not a lattice. You get this kind of diagram, and this translates. It's within a full correspondence with here. You have the fundamental group of your manifold. Here, let's say this is the universal cover. We call it X. This is the trivial group, and here it's the diagram of subgroups. There's a full correspondence between this and this. This means, here, this already tells you the translation from the geometrical to the algebraic problem. You want to find coverings of manifolds, start with a base manifold, take a fundamental group, and take its subgroups. Or alternatively, if you don't want to start with the manifold and take the fundamental group, start with a symmetric space, a nice space simply connected, find an action, a discrete action on it, quotient by that action to get this, and do the same thing. Whoever was in my last week. So.
We want to get a nice family of groups, not just...
It's a sequence of subgroups. Each subgroup will correspond to a cover. Each one gives you a manifold. Each manifold gives you a complex. Well, each manifold you have this natural triangulation. This gives you the code.
So you take like congruent subgroups?
So what can Goose do? That's like probably the most natural thing to do. Let's just show first. Before that, let's show an example. Here, this is kind of like an exercise, okay? So we had the toric code. We started with the torus, and we said that's a terrible code. This was a very bad code, okay? So let's try to improve it by finding coverings. Let's not take the torus, but let's maybe when we go up and up, it will get better. And I claim it doesn't get better. And what's the best way to see it? What is the fundamental group of the torus? It's Z times Z. This doesn't have interesting subgroups, okay? If you want finite, we only consider finite coverings, right? Finite coverings in order to get compact manifolds. So this means finite index subgroups here. Basically, you'll have, let's say you can have 2Z times Z. This is a subgroup inside here, but it's basically a Z times Z. This means that all the finite covering of the torus is a torus. It's just maybe a bigger torus. So you can make the torus bigger and bigger and bigger. The homology will still stay the same homology. All the point is that when you go higher and higher, you get more. The homology group grows. So we can't. We have nothing to do here with the torus. You can't improve it. Okay, and you see it's very easily on the subgroups. But let's do more sophisticated stuff. So let's, even though we know that two-dimensional will not give us good stuff, let's still take the hyperbolic space. We know this is SL and R modded by SO N.
That's 2 in this case.
Only for 2.
It's H2.
Yeah. Okay. And so we start with this. This is a nice space, and we quotient it by SL and Z. We call this. Yeah. We call it. Okay. So this is the. Let's draw it nicely. This is the hyperbolic plane. This is the fundamental domain, and this folds into a thing that I still don't understand. Okay? So we get here, it's actually not a manifold, but it's something else. And this, we call this M0. This is a covering map. The fundamental group is exactly the lattice which we started with. Okay? But we want now a sequence. Okay? We want.
So what is it that you don't understand about it?
Hmm?
The cusp? You do understand because you saw the pseudosphere.
No, I don't. This is not even. I don't understand how can something a topological space have a fundamental group that is SL2Z? How does it look like? I don't understand how to.
I mean, just but do you have a pillow?
Huh?
In your bed, do you have a pillow?
Yeah.
Does it have this corner thing?
Yeah.
That's how it looks like. I mean, it's.
How can a pillow have an SL2Z?
No, you can think of SL2Z as Z mod 4 free product with Z mod 6, right?
Okay.
You can think of a surface of a topological space with Z mod 4 as fundamental group, Z mod 6 as a fundamental
And
group.
take the product.
It's a Van Kampen.
But doesn't, I mean, if I understand the gluing right, it doesn't it have trivial fundamental group?
No, definitely not trivial because this goes here to infinity, so it looks more like you definitely have this loop. I don't really know where you get where is the other generator? Okay, I mean you have two generators for
in
SL2Z.
this corner of the pillow.
Yeah.
Right here.
Yeah.
Yes.
This is it.
Yeah.
That and the center, the top part of the circle.
No.
This?
על הקשת, באמצע הקשת.
כאן?
באמצע.
Yeah, the midpoint of that, yeah.
This one.
למעלה?
Okay.
Just
Okay.
What's the first?
The two
Corner?
corners, right? The two things, they are identified when you.
So you mean this thing?
That line is identified with this horizontal.
These two arcs. So down this central point, these two arcs are getting identified.
Okay.
When you.
So you're saying that this is a loop, or even no, it's
you
smaller
have,
than that.
you have to
Yes, this is a loop.
try
I mean,
to
half of this arc is a loop.
Yeah. But isn't it topologically a disk?
What?
After you glue everything.
Yes, topologically it is this. But then you forget the geometric structure.
Yeah.
You need to define here the fundamental group of an orbifold. This is not something you did learn in your I don't know, kindergarten topology.
Yes. Okay.
Yeah, this is not a manifold, so it's not a disk in that sense. There are these two special points over here where you cannot measure angle up to 360 degrees.
But fundamental group, you don't need geometry, do you? You just need topology.
But you can make another notion of fundamental group of a geometric object.
Yeah.
Of an orbifold.
Of an orbifold.
So does orbifold does it have all the properties, topological properties such as is it locally connected and semi-locally simply connected in order to have this covering theory?
It is everything. It is just
So
a topological space as topological space for which you do cover theory R, plus some extra special points, and to those special points one attaches fine groups. So you can come up with a theory of fundamental groups of topological spaces with special points with finite groups attached to these points.
Does it coincide with the notion of fundamental group of this is just a topological space?
No.
As
topological space, this is compactable as a.
Okay, so this makes much more sense.
Yeah. Okay, as topological space, it is contactable.
Okay.
It is your pillow when you cut one. I mean, when you open. Oh, it is your pillow. It is open.
I think it's just very confusing to call it a fundamental group.
It is open, no?
It sounds to me just very confusing to call it a fundamental group if it's not a fundamental group. But I don't know. It's.
Did we discuss fundamental groups of graphs?
No.
Yeah.
Did Gil?
Yes, she did.
No, I think last semester. This
Last semester?
Yeah.
Okay, you haven't been here. Okay, your fault.
Yeah.
Maybe, I mean, our time is almost up, so maybe you want to finish up with something.
Yeah. It's actually very short, so I can do it. We had this example. This example doesn't work, and we want to just see a nice way of constructing subgroups. So this space, the fundamental group is SL2Z. We want subgroups, finite index subgroups inside SL2Z, and we want to think of a way of doing this. Okay. So in this case, for example, if we think of it, how do we construct finite index subgroups? We think of Z instead of Z, we do NZ, right? Or here we take MZ or something like that. So the same idea we're going to do here. So the idea is as following. This is SL2, and here we can put Z, but we can put any ring with identity. Okay? Now this is a functor from rings with identity into groups. You plug in a ring with identity, you'll always get a group. Okay? And it's a functor.
Such functors called group schemes.
Group schemes.
So SL2 is a group scheme.
Okay.
Or algebraic groups, actually. That's another name.
Yeah. And so what does this mean? This means that if you plug in a ring, you'll get a group. And if you plug in a ring homomorphism, so you have SL to R1 and SL, if you have R1 to R2, call this phi, we'll get phi star from SL in R1 to SL to R2. So we can do the same idea there with when we have this, because we have this homomorphism. And this gives us this. So basically, okay. And what so here, when we take Z inside Zn, what we were interested is in the kernel of this map, which is NZ. Right? We'll do the same thing here. We'll define gamma n to be the kernel of this map, which is basically taking SL2Z, but thinking of it mod n, okay? All the entries are mod n, okay? And you can do this for any n. So you get, and each one will be a finite index subgroup. I think it's not hard to say that it's finite index
so
subgroup.
just explicitly, gamma n is the 2x2, the group of 2x2 matrices with integer coefficients, and the entries will be 1 mod n on the diagonal and 0 mod n off the diagonal.
Yeah, exactly. I think it's true to say that it's exactly elements. Take the identity, take any matrix in SL2Z, but with some product n. This is how elements here look like. So it's really a natural generalization of NZ.
I mean, the matrix should be not necessarily in SL2, right? The T need not be in SL2. It should be.
You're right.
N plus 1 is in
GLZ or no. No, even not. Yeah, it can be just matrices
with integer coefficients,
integers, yeah.
such that 1 plus nt is an SO2.
Right. Yeah. Okay. Okay, I think we will finish.
Excellent.
Questions?
So, next time